Now let's look at bonding that occurs when electrons are shared. Ionic bonding comes from electrons being transferred from a metal to a nonmetal. But in covalent bonds, we share electrons. Covalent bonding is typically found between two nonmetals. And we see covalent bonding when we see molecular species or substances that are made of molecules. Atoms bond together to form molecules. And this is as opposed to ionic compounds where ions are bonding together. So here it's atoms bonding together to form molecules. This is a very strong attraction. And atoms share pairs of electrons to attain octets. Now between molecules, there's generally a weak attraction between molecules, but the atoms in a molecule are very strongly attracted to one another. Now, as we said, nonmetal atoms often bond to achieve an octet of valence electrons by sharing electrons. Metals always have to lose electrons, but nonmetals can gain electrons or they can share. Now, there are exceptions to the octet rule, which we will get to, but in the Lewis theory, atoms share electrons to complete their octet to get the stable 8 valence electrons of the noble gases. Now, to get this, they can share electrons with more than one atom, or they can share several pairs of electrons with the same atom. So let's take a look at some of the possibilities. Single covalent bonds occur when two atoms share one pair of electrons. And so here's an example of a single covalent bond. Fluorine atoms have 7 valence electrons, and if they share their lone electron, it becomes 2 electrons, and they gain an octet. We often signify these shared electrons as a line to distinguish them from the electrons that are not being shared. Here's another example of shared electrons. Oxygen has 6 valence electrons and hydrogen has 1. If hydrogen shares its 1 electron with the unpaired electron on oxygen, oxygen gets an octet of electrons and hydrogen gets 2 electrons just like helium. And again, we show these shared electrons often as lines. Each line represents 2 electrons being shared. And when we count the total number of electrons that each atom has, we count the shared pair for each. So hydrogen has 2 electrons, hydrogen has 2 electrons, and oxygen has 8. 2, 4, 6, 8. And each fluorine here has 8. 2, 4, 6, 8. 2, 4, 6, 8. Double bonds occur when 2 atoms share 2 pairs of electrons or a total of 4 electrons. Double bonds are shorter and stronger than single bonds. So here's an example. We have 2 oxygen atoms, and oxygen has 6 valence electrons, 2 unpaired electrons. When these 2 electrons share with the 2 electrons from another oxygen atom, we have a total of 4 electrons being shared, or what's known as a double bond. And when we do that, oxygen now has an octet. If only 2 electrons were involved, then each oxygen would not have a total of 8. We need to share 4 total so each oxygen can have 8. 2, 4, 6, 8. 2, 4, 6, 8. And this is how oxygen exists in the molecular form with as a diatomic atom, and this is why it's diatomic, not a diatomic atom, sorry, a diatomic molecule, and this is why it's a diatomic molecule, because when it forms this double bond, each oxygen has the stable octet of electrons. And then a little bit more rare is the triple covalent bond. This is where we have 2 atoms sharing 3 pairs of electrons, or 6 total electrons. And this is shorter and stronger than a single or a double bond. So here we have nitrogen with 5 valence electrons, 3 of them unpaired. When these 3 electrons share with the other 3 electrons from the other nitrogen atom, we have a triple bond, and each nitrogen has a total of 8 electrons around it. 2, 4, 6, 8. 2, 4, 6, 8. And this is why nitrogen exists as a diatomic molecule, because when it has this triple bond, each nitrogen has 8 electrons, the stable noble gas valence electron configuration. Now, one thing that we're going to be distinguishing between in these Lewis dot structures of molecules is between bonding and lone pair electrons. Electrons that are shared by the atoms are known as bonding pairs, and electrons that are not shared by the atoms are called lone pairs or non-bonding pairs. So, the atoms that are being, the electrons that are being shared between oxygen and sulfur are the bonding pairs. This would be a bonding pair as well. And the electrons that are not being shared are lone pairs. So if we look back here, this would be a lone pair, and 3 bonding pairs. Now, the more electrons 2 atoms share, the stronger they're bonded together. So triple bonds are stronger than double bonds, stronger than single bonds. And they are also shorter because they are sharing more electrons and more closely attracted to one another. The carbon and nitrogen nucleus are closer to one another in a triple bond than they are in a double bond, and closer to one another in a double bond than in a single bond. And here's some experimental data. Here's a typical bond length between a carbon-carbon single bond, 154 picometers. The typical bond length between a carbon-carbon double bond is shorter, and a carbon-carbon triple bond is even shorter. Now, bond energy is defined as the minimum energy required to actually break this bond. And a single bond requires 346 kilojoules to break 1 mole of carbon-carbon single bonds. A carbon-carbon double bond requires almost double the amount of energy per mole, and then a carbon-carbon triple bond requires even more per mole. So we can see how strong these interactions are by how much energy is required to break them. And we see the same trend between any 2 atoms that we look at. As the number of electrons being shared increases, the bond length decreases, and the energy increases to break them. Now, before we go any further, let's take a look at polyatomic ions. Polyatomic ions are ions made up of more than 1 atom. And how are these atoms held together? They are actually held together by covalent bonds, but they have an unequal number of electrons and protons, and so they have an overall charge. So here's an example of cyanide. There's a triple bond holding the carbon and the nitrogen together, but if we count all the valence electrons involved here, there's going to be 1 more electron than we would get by just counting the valence electrons of carbon and nitrogen. So that extra valence electron added on allows carbon and nitrogen to bond in such a way such that the octet rule is fulfilled. But polyatomic ions maintain the carbon and nitrogen stay together all the time for cyanide, and they always have this -1 charge, and they can exist in a crystal lattice with a cation to form an ionic compound, even though the polyatomic ion is made up of covalent bonds. Its overall charge makes it able to bond with other cations to form ionic bonds.